Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. For as long as humans watched birds trace patterns across open sky, the impulse existed to join them, to break free from the surface that held every footstep, every journey, every boundary of human experience. The dream was ancient, appearing in myths and legends across cultures separated by oceans and centuries, yet united in their longing to overcome the fundamental constraint of terrestrial existence. What birds accomplished with hollow bones and feathered wings, what insects managed through rapid oscillations too fast for the eye to follow, remained beyond human capability, despite endless observation and speculation. The limitation was not merely physical, but philosophical. Humans belonged to the ground in ways that shaped every aspect of existence. Cities grew horizontally, spreading across plains and up hillsides, but never extending into the space above, except for the heights that structures could reach before their own weight became insurmountable. Travel followed the topology of land, constrained by mountains, channeled along valleys, halted by bodies of water too wide to bridge or too deep to ford. The third dimension existed as a domain of weather and wind, of clouds and celestial bodies, but not as a space humans could occupy or traverse. Yet the practical advantages of flight were obvious to anyone who considered them. A bird traveling between 2 points could ignore terrain entirely, taking the direct path through air while earthbound travelers negotiated whatever obstacles lay between origin and destination. Distance measured in straight lines differed dramatically from distance measured along available routes, and the difference represented time, effort, and limitation. A mountain range that required days to cross by foot or horse presented no obstacle to a bird that could simply rise above it and glide down the far side. Military minds recognized these advantages with particular clarity. The ability to observe enemy positions from above would provide information impossible to obtain from ground level, where vision extended only to the nearest ridge or tree line. The possibility of delivering weapons from above introduced vulnerabilities that no fortification designed against ground assault could address. The speed of aerial movement would allow forces to concentrate or disperse in ways that would confound conventional military planning. These strategic considerations created incentives for solving the problem of flight that went beyond mere curiosity or the satisfaction of achieving the seemingly impossible. Commerce, too, would benefit from aerial transport. Valuable goods that justified the cost of rapid delivery could move between cities without regard for the condition of roads or the availability of railway connections. Messages and documents could travel at speeds that would make current methods seem glacial by comparison. The time saved would compound into economic advantages for those who could exploit aerial routes, while competitors remained bound to surface transportation. The potential returns justified substantial investment in pursuing solutions to technical problems that seemed, from a distance, nearly insurmountable. The scientific community approached flight as a problem in physics and engineering. Forces needed to be understood and quantified. Materials needed to be evaluated for their properties under stress. Principles needed to be derived that would guide the design of structures capable of supporting themselves in air while carrying useful loads. The fact that birds accomplished this naturally suggested that physical laws permitted it, that some combination of shape and motion and structural efficiency could produce the necessary forces to overcome gravity and achieve controlled movement through three-dimensional space. But observation of bird flight revealed complexity that defied simple analysis. Wings flexed and twisted during the flight cycle, changing shape in ways that seemed related to the forces being generated, but were difficult to measure or understand in detail. The feathers themselves had intricate structures, barbs and barbules interlocking to create surfaces that were both flexible and resistant to air passage. The muscles that powered flight were proportionally much larger than human musculature, suggesting that achieving flight would require either greatly increasing the power available or greatly reducing the weight that needed to be lifted. The dream persisted despite the difficulties, fed by each small advance in understanding and by the occasional individual who convinced themselves they had discovered the secret, constructing devices that invariably failed to achieve sustained flight, but kept the possibility alive in public imagination. These failures did not discourage the dreamers. They merely refined the questions, narrowed the range of approaches worth pursuing, eliminated methods that demonstrably could not work, while leaving open the hope that some other approach might succeed where previous attempts had failed. The problem presented itself in layers, each of which needed solution before the next could be meaningfully addressed. First came the question of generating lift, the upward force that would need to exceed the weight of any flying device and its occupant. Air itself seemed too insubstantial to support weight. Yet birds demonstrated that properly shaped surfaces moving through air could generate forces adequate to hold them aloft. The challenge was understanding what made those surfaces effective and how to replicate their function with materials and construction methods available to human builders. Second came control, a device that could rise into the air but could not be steered, would be useless for practical purposes and dangerous to anyone aboard. Birds adjusted their flight path through subtle changes in wing angle and tail position, maintaining stability through constant small corrections that happen too quickly for conscious thought. A human pilot would need mechanisms that translated intended maneuvers into the necessary adjustments of control surfaces, and these mechanisms would need to respond precisely and reliably, or the attempt at controlled flight would end in an uncontrolled fall. Third came propulsion. Birds used muscle power to flap wings, but the power-to-weight ratio of human muscle made this approach impractical for human flight. Some other method of generating forward motion would be needed, either a more efficient means of converting human effort into thrust or an external power source, light enough to be carried aloft, yet strong enough to propel a flying device at speeds sufficient for lift generation. The engines being developed for ground vehicles were far too heavy relative to their power output, and no other prime mover existed that could meet the requirements. Fourth came construction. Any flying device would need to be light enough that achievable lift forces could overcome its weight, yet strong enough to withstand the stresses of flight without structural failure. Materials that were strong tended to be heavy. Materials that were light tended to be weak. Finding combinations that provided adequate strength at minimal weight required understanding material properties in ways that builders of ground-based structures never needed to consider. A bridge that was heavier than necessary was merely inefficient. A flying device that was heavier than necessary could not fly at all. The study of birds provided clues, but not blueprints. Bird bones were hollow, reducing weight while maintaining structural integrity through clever internal bracing. Bird bodies were streamlined, minimizing resistance to motion through air. Bird wings combined flexibility with resistance to bending, achieving shapes that adjusted to flight conditions while maintaining their essential function. But birds were the product of millions of years of evolution, optimized by countless generations of variation and selection. Human designers would need to achieve in years or decades what natural selection had accomplished across geological timespans. Wind offered both obstacle and opportunity. The currents that buffeted anyone standing on an exposed hilltop carried energy that, if properly harnessed, might contribute to flight. Birds used wind to soar, gaining altitude without flapping, riding invisible columns of rising air to heights they could never reach through muscle power alone. But wind was unpredictable and variable, sometimes aiding flight and sometimes making it impossible. And any practical flying device would need to function across a range of conditions rather than only when conditions were optimal. The imagination generated designs that looked plausible on paper, but failed when built. Wings too small to generate adequate lift at speeds that could be achieved. Control surfaces too small to overcome the moments that would spin a device out of control. Structures too weak to resist the forces of rapid air movement. Power sources too feeble to overcome drag. Each failure taught lessons, but the lessons accumulated slowly because testing required construction, and construction required resources that were often unavailable to those obsessed with solving the problem of flight. Yet, the impulse would not die. Every successful test, however brief, every improvement in understanding, however incremental, fed the belief that human flight was achievable, not through magic or supernatural intervention, but through careful application of mechanical principles and patient refinement of designs. The dream was beginning to acquire the solidity of engineering problem, rather than remaining pure fantasy. And that transformation, subtle as it was, marked the beginning of the path from impossible to inevitable. The earliest attempts to achieve flight mimicked the most obvious aspect of bird motion, the flapping of wings. Inventors constructed frames of wood and fabric that resembled bird wings in gross form, attaching them to harnesses that would allow a human operator to move them up and down through arm and leg power. These ornithopters, as they came to be called, were based on the reasonable assumption that since birds flew by flapping wings, humans could do the same if given appropriately designed wings to flap. The attempts failed consistently and sometimes catastrophically. A human perched on a tower or cliff edge, strapped into a wing apparatus, would leap into space and immediately discover that the muscles required for sustained wing flapping were absent from human anatomy. The descent that followed was rapid and uncontrolled, ending in impacts that ranged from painful to fatal, depending on the height of the launch point. The human body lacked both the power and the structural adaptations that made flapping flight work for birds. The massive pectoral muscles, the rigid skeletal attachments, the metabolic capacity to sustain intense effort. Some experimenters recognized that flapping might not be necessary if forward motion could be achieved by other means. They studied soaring birds that rode wind currents without flapping, maintaining altitude through subtle adjustments of wing angle and body position. These observations suggested that fixed wings might generate lift if air moved past them at sufficient speed, transforming the problem from one of mechanical flapping to one of forward propulsion and control. The shift in thinking was subtle but significant. It separated the function of lift generation from the mechanism of propulsion. Gliders emerged from this insight, unpowered devices with fixed wings that could be launched from slopes or towed to speed, achieving brief periods of controlled descent that resembled true flight. The builders of these gliders learned through direct experience how different wing shapes affected performance, how control surfaces needed to be positioned and sized, how weight distribution influenced stability. Each flight provided data that informed the next design iteration, gradually accumulating practical knowledge about what worked and what failed. The control problem revealed itself as more complex than initial estimates suggested. A glider needed to maintain stability in turbulent air while also responding to pilot inputs that would change direction or altitude. Too much stability and the device would not maneuver. Too little and it would tumble unpredictably. The balance required careful design of tail surfaces, wing geometry, and control mechanisms that the pilot could operate without excessive force or complexity. Some designs used weight shifting. The pilot moved their body to change the center of gravity. Others used movable surfaces attached to the wings or tail that could be angled to change the forces acting on different parts of the device. Testing happened in remote locations where crashes would not endanger bystanders, and where wind conditions could be studied through repeated trials. Hills facing prevailing winds provided the slopes needed for launches, and the open spaces beyond gave room for landings that might be rough or off-target. The experimenters became familiar with the feel of wind on their faces, learned to read the movement of grass and leaves as indicators of air currents, developed intuitions about when conditions were suitable for testing and when they were too dangerous to risk. Materials available for construction were limited by the requirement that everything be as light as possible while maintaining adequate strength. Wood provided the primary structural material, light for its strength when pieces were properly shaped and oriented to resist the expected loads. Fabric covered the wings, stretched tight over the wooden frame, and treated with compounds that made it resistant to air passage while adding minimal weight. Wire bracing connected structural members, creating triangulated frameworks that resisted deformation while using minimal material. The construction techniques resembled those used for building delicate furniture or musical instruments more than those used for building machinery. The mathematics of flight began to emerge from systematic measurement and analysis. Experimenters measured lift forces generated by different wing shapes at various angles and speeds, creating tables of data that revealed relationships between these variables. They studied drag, the resistance to forward motion through air, and learned that streamlined shapes experienced far less drag than blunt ones. They investigated stability, discovering that the location of the center of pressure relative to the center of gravity determined whether a disturbance would grow or diminish. The accumulation of quantitative knowledge transformed flight from an art based on intuition to a science based on measurable principles. Wind tunnel testing allowed controlled experimentation that natural wind could not provide. A fan forced air through a chamber where models could be mounted and forces measured with scales and indicators. The conditions could be varied systematically: speed, angle, wing configuration, and the results recorded for analysis. This technique eliminated much of the risk and expense of full-scale testing while providing data that could guide design decisions. The models themselves needed to be carefully constructed to match the proportions of full-scale designs, and the interpretation of results required understanding how effects would scale when dimensions increased. The propulsion problem resisted solution longer than lift and control. Human muscle power was inadequate for sustained flight, and no mechanical alternative existed that provided sufficient power at acceptable weight. Steam engines were far too heavy. Spring mechanisms stored insufficient energy. Compressed air containers were heavy and provided limited duration. The absence of a suitable power source constrained early aircraft to gliding, descending through air in controlled fashion, but unable to climb or sustain level flight for more than brief periods. The dream of free flight, traveling from one place to another by air rather than merely descending from a high point to a lower one, remained unachievable without solving the propulsion problem. Internal combustion engines offered a potential solution once their development for ground vehicles demonstrated that they could be built light enough and powerful enough to justify their weight. The adaptation of these engines for aircraft use required extensive modification. Cooling systems needed redesigned to function in the variable conditions of flight. Fuel systems needed to work regardless of the aircraft's orientation. The engines needed to maintain operation through vibrations and accelerations that ground use never encountered. The propeller, a rotating wing that generated thrust by accelerating air backward, needed to be designed to convert engine power into forward motion efficiently, and this required understanding airfoil theory and applying it to the unique conditions of a spinning blade. The propeller design problem was subtle. Each section of the blade moved at a different speed relative to the air, faster at the tip than near the hub, and needed a different angle to operate efficiently at its particular speed. The blade needed to be strong enough to resist the forces generated during operation without being so heavy that it absorbed excessive power just to spin itself. The number of blades, their width and chord length, the overall diameter, all of these parameters affected performance and needed to be optimized together rather than independently. Early propellers were crude, wasting much of the engine's power, but they improved rapidly as builders learned to apply the same principles that governed wing design. The problem of stability divided into two categories: longitudinal stability, governing pitch up and down, and lateral stability, governing rolling and yawing motions. Each required careful consideration of how surfaces were sized and positioned. The tail surfaces provided damping that prevented oscillations from growing, while the wing design determined how the aircraft responded to disturbances. Some early designs were inherently unstable, requiring constant pilot attention to prevent departures from controlled flight. Others were too stable, resisting maneuvers the pilot attempted to command. The optimal balance depended on the intended use. A stable aircraft was easier to fly but less maneuverable. An unstable aircraft could turn quickly but demanded skill and attention. Launches evolved from running starts down slopes to more sophisticated methods that reduced the risk and complexity of getting airborne. Rail systems allowed an aircraft to accelerate along a track until it reached flying speed, then released to climb away from the ground. Elastic cords or falling weights provided initial acceleration that supplemented engine power during the critical moment of takeoff when speed was lowest and power demands highest. Some designers experimented with skids or wheels that would roll along the ground during the takeoff run, supporting the aircraft until it generated enough lift to fly. Each method had advantages and disadvantages, and the choice depended on the specific design and available facilities. Landings presented different challenges. An aircraft descending toward the ground needed to reduce speed to safe levels without losing the lift that kept it airborne until the moment of contact. The technique of flaring, raising the nose just before touchdown to increase angle of attack and generate additional lift while bleeding off speed, required timing and judgment that came only with practice. Landing surfaces needed to be smooth and clear of obstacles, long enough to allow deceleration after touchdown, and aligned with wind direction to minimize crosswind forces during the approach. The unpredictability of wind gusts at low altitude made every landing a test of skill and sometimes luck. The community of experimenters remained small, but gradually became more connected as publications shared results and techniques. Technical journals carried descriptions of tests and designs, allowing others to learn from successes and failures without repeating every mistake themselves. Occasional gatherings brought builders together to compare approaches and debate theories, creating informal networks of knowledge exchange that accelerated progress. The culture was one of sharing rather than secrecy, perhaps because the goal seemed large enough that collaboration served everyone's interests better than competition would have. The challenge was humanity's challenge, not a race between individuals or nations, at least not yet. The transition from brief hops to sustained flight required refinement of every component and system until they functioned together with sufficient reliability that failures became exceptional rather than routine. Early powered flights lasted seconds and covered distances measured in tens or hundreds of feet, constrained by control difficulties, power limitations, and structural weaknesses that revealed themselves only under the stresses of actual flight. Each successful flight provided confidence and data. Each failure revealed problems that needed solving, and the accumulated experience gradually extended the envelope of what was achievable. The airframe needed to resist forces from multiple directions simultaneously, lift pulling upward on the wings, weight pulling downward on the structure, drag pushing backward against forward motion, thrust pushing forward from the propeller, and dynamic loads from turbulence and maneuvers. Wood framing created the skeleton, with members sized and oriented to carry their specific loads. Wire bracing provided tension elements that prevented the frame from distorting under asymmetric loads. The covering, fabric stretched over the frame and treated to resist air passage, contributed to strength by distributing loads and preventing local buckling. The entire structure needed to function as a system where each element contributed to overall integrity. Joints between structural members represented potential failure points where stress concentrated and where construction quality determined whether the connection would hold or fail. Glue joints required proper preparation of surfaces and correct proportions of adhesive, with inadequate bonding leading to separation under load. Mechanical fasteners needed to be sized appropriately and installed carefully to avoid crushing wood fibers or creating stress concentrations. The craftsmanship of construction mattered as much as the correctness of design. A well-designed joint poorly executed would fail, while a mediocre design executed with skill might hold. Builders learned these lessons through failures that sent aircraft crashing and through the examination of wreckage that revealed where and why structures had given way. Engine reliability improved through the same iterative process that refined airframes. Early engines failed frequently, overheating, seizing, losing power at critical moments. The causes were many. Inadequate lubrication allowing bearing surfaces to contact and weld, vibration loosening connections and fracturing components, fuel delivery inconsistencies, starving cylinders, or flooding them, ignition systems failing to spark reliably. Each mode of failure required a specific solution, and the accumulation of these solutions gradually produced engines that could run for hours rather than minutes, that could be trusted to continue operating rather than being expected to quit at any moment. Propeller efficiency improved as designers learned to match blade geometry to specific operating conditions. The twist along the blade length, the chord width at different stations, the airfoil section used, the overall diameter. These parameters were optimized through testing that measured thrust produced at various speeds and power levels. Propellers designed for takeoff generated maximum thrust at low speeds, but became inefficient at higher velocities. Propellers designed for cruising flight performed poorly during takeoff. The compromised designs that performed adequately across the full range of flight conditions required careful balancing of competing requirements. The material choice mattered too. Wood propellers needed grain orientation that resisted splitting under centrifugal loads, and the wood needed to be dense enough for strength, yet light enough to avoid excessive weight. Control systems evolved from simple cables and pulleys to more sophisticated linkages that provided the pilot with sufficient mechanical advantage to move control surfaces against the aerodynamic forces acting on them. A control surface that was easy to move at low speed might become impossibly stiff at higher speeds as dynamic pressure increased. Mechanisms that multiplied the pilot's force allowed control authority to be maintained across the speed range, though at the cost of reduced sensitivity that made precise inputs more difficult. Balancing tabs, small surfaces attached to trailing edges of control surfaces, used aerodynamic forces to reduce the effort required for deflection, creating systems that remained manageable throughout the flight envelope. Instrumentation appeared as aircraft became capable of extended flight, and as pilots needed information beyond what they could sense directly. Airspeed indicators measured the pressure difference between static and dynamic conditions, translating this into a reading that indicated velocity relative to the surrounding air. Altimeters measured atmospheric pressure and converted it to altitude above sea level, providing information about height that was difficult to judge visually once beyond the immediate vicinity of the ground. Engine instruments monitored oil pressure, temperature, and rotational speed, warning of conditions that might lead to failure if not corrected. The instruments themselves needed to function despite vibration, operate across temperature ranges encountered at different altitudes, and present information in forms that pilots could read quickly and interpret correctly. Navigation remained primitive by later standards. Pilots followed visible ground features, used compasses that were often unreliable in the magnetic environment of an aircraft, and estimated position based on elapsed time and estimated ground speed. The absence of radio navigation aids meant that flights in poor visibility or over featureless terrain were dangerous, and the risk of becoming lost was substantial. Pilots learned to read landscapes from above, recognizing rivers, railways, towns, and other features that could serve as checkpoints. The planning of routes required considering the availability of these reference points and having alternative plans for cases where visibility degraded unexpectedly. Weather influenced flight operations in ways that pilots gradually learned to respect. Wind at altitude differed from wind at the surface, sometimes dramatically, affecting ground speed and drift from intended course. Temperature decreased with altitude, influencing engine performance and creating conditions where moisture in the air could condense on control surfaces or in fuel lines. Storms and turbulence created forces that could overwhelm control authority or exceed structural limits. The absence of reliable weather forecasting meant that pilots often encountered conditions they had not anticipated, learning through experience which situations could be safely navigated and which required immediate landing or a return to base. Training methods developed as flight became sufficiently reliable that students could practice without excessive risk of injury or death. Early pilots were self-taught, learning through trial and error with no instructor to guide them beyond the written descriptions and diagrams that captured previous experience. As the community of pilots grew, knowledge could be transferred more directly through demonstration and supervised practice. Students learned to taxi aircraft on the ground before attempting flight, developed feel for the controls in low-risk situations, and progressed gradually to more complex maneuvers as their skill increased. The training aircraft themselves were often modified to reduce performance to levels that gave students more time to react and recover from errors. Maintenance practices emerged from the recognition that aircraft required regular inspection and service to remain airworthy. Fabric covering needed to be checked for tears and deterioration. Wire bracing needed to be tensioned correctly. Too loose and it would not provide support. Too tight and it would overstress the structure. Wooden members needed inspection for cracks that could propagate into complete failures. Engines needed oil changes, valve adjustments, and examination of internal components for wear. The maintenance schedule balanced the need for thorough inspection against the desire to maximize flight time, with critical items checked before every flight and less critical ones inspected at longer intervals. Materials science advanced partly in response to the demands of aircraft construction. Alloys with better strength-to-weight ratios were developed, allowing metal to replace wood in highly stressed components. Fabrics were woven with tighter weaves and treated with compounds that improved their durability and resistance to environmental degradation. Adhesives were formulated to maintain bond strength despite temperature variations and vibration. The testing of materials became more rigorous, with samples subjected to loads and conditions that simulated service use to verify that they would perform adequately throughout their expected lifetime. Manufacturing techniques scaled up from one-off custom construction to production methods that could produce multiple aircraft with consistent quality. Jigs and fixtures ensured that components were built to identical dimensions, allowing parts from different production batches to be interchangeable. Assembly sequences were organized to minimize wasted motion and reduce the time required to complete each aircraft. Quality control procedures verified that critical dimensions and strengths met specifications before components were installed. The transition from craft production to industrial manufacturing reduced costs and increased availability while requiring new skills and organizational methods. Documentation systems captured the knowledge that had been accumulated through experience and testing. Design drawings specified dimensions and materials with precision, allowing others to build from plans rather than having to reverse engineer from existing examples. Maintenance manuals described inspection procedures and service intervals, standardizing the care that aircraft received. Operating handbooks provided pilots with performance data and limitations, reducing the need for each pilot to discover through personal experience what the aircraft could and could not safely do. This codification of knowledge accelerated the spread of aviation beyond the small community of pioneers who had developed it through years of experimentation. Safety practices developed in response to accidents that revealed hazards not previously recognized. Pilots learned to verify fuel quantity before flight after several forced landings resulted from inaccurate estimation of remaining supply. Pre-flight inspections became routine after structural failures traced to damage or wear that visual examination would have detected. Restrictions on flight in marginal weather emerged after accidents demonstrated that pilots with limited experience and inadequate instruments could not maintain controlled flight in conditions where the horizon was not visible. Each improvement came at cost, often the injury or death of someone who encountered a hazard before it was widely understood. But the accumulation of these lessons gradually reduced the frequency and severity of accidents. The regulatory environment began to take shape as governments recognized that aerial activity could affect public safety and national security. Requirements for aircraft registration created records of ownership and accountability. Pilot certification programs verified minimum competency before granting permission to fly. Airspace restrictions protected sensitive areas and prevented conflicts with ground-based activities. The regulations reflected both safety concerns and the interests of established authorities in controlling a new domain of human activity. The aviation community generally accepted these constraints as reasonable, recognizing that some level of oversight was necessary as aircraft became more numerous and capable. The engine that powered flight was a machine of remarkable complexity, converting the chemical energy stored in liquid fuel into rotational motion through a sequence of precisely timed events that repeated thousands of times each minute. Inside each cylinder, a piston moved up and down within machined walls, compressing a mixture of fuel vapor and air into a small volume at the top of its stroke. A spark arrived at the instant of maximum compression, igniting the mixture, and the resulting expansion drove the piston downward with force that was transmitted through a connecting rod to the crankshaft, where linear motion became rotation. The crankshaft itself was a study in mechanical engineering, shaped with offset journals that converted the reciprocating motion of multiple pistons into smooth rotation. The timing of each piston stroke was offset from the others so that power delivery overlapped, reducing the pulsing that would otherwise create vibration. The shaft needed to be stiff enough to resist twisting under the torque loads imposed by combustion events, yet light enough that rotating it did not consume excessive power. Counterweights opposite the crank throws balanced the reciprocating masses, reducing the shaking forces that would otherwise stress the engine mounts and disturb the airframe. Valves controlled the flow of gases into and out of the cylinders with timing that was critical to engine performance. The intake valve opened just before the piston began its downward stroke, allowing the fresh charge to enter as the descending piston created vacuum. It closed after the piston had reversed direction and begun compressing the mixture, trapping it inside the cylinder. The exhaust valve opened near the end of the power stroke, releasing burned gases before the piston rose again to push the remaining exhaust out through the open valve. The camshaft that operated these valves was driven from the crankshaft through gears or chains, maintaining the precise relationship between piston position and valve timing. Cooling extracted the heat that would otherwise raise metal temperatures beyond their capacity to maintain strength. Air-cooled engines used fins cast or machined into cylinder walls to increase surface area, relying on airflow during flight to carry heat away. The fins needed to be sized to provide adequate cooling at cruise speed without creating excessive drag, and their spacing had to allow air to flow between them without obstruction. Liquid-cooled engines circulated water or other fluid through passages in the cylinder walls, carrying heat to a radiator where air passing through thin metal tubes absorbed the thermal energy. The cooling system added weight and complexity, but allowed more compact engine packaging and more uniform temperature control. Lubrication prevented the metal-to-metal contact that would rapidly destroy sliding and rotating surfaces. Oil was pumped through passages drilled in the crankshaft and engine block, reaching bearings, cylinder walls, and valve mechanisms under pressure. The oil formed a thin film between moving parts, supporting loads through fluid pressure while allowing relative motion with minimal friction. The oil also served as a coolant for internal components that could not be reached by external cooling, and it carried away particles of wear debris that would otherwise accelerate degradation. The oil itself degraded through exposure to heat and contamination, requiring periodic replacement to maintain its protective properties. The carburetor mixed fuel with air in proportions that varied with engine power demand and atmospheric conditions. At idle, a small orifice provided a rich mixture that would burn reliably despite low airflow velocity. At full power, larger passages delivered greater fuel quantities to match the increased air consumption. The pilot controlled mixture through a lever that adjusted the fuel flow, compensating for the reduction in air density at higher altitudes where less oxygen was available for combustion. Getting the mixture correct was essential. Too rich and fuel was wasted while power suffered. Too lean and combustion temperatures rose to levels that could damage pistons and valves. Ignition systems generated high voltage sparks that jumped across gaps in spark plugs, igniting the compressed fuel-air mixture at the precise moment when the piston neared top dead center. The timing of ignition advanced with engine speed, firing earlier in the compression stroke as rotational velocity increased so that combustion pressure peaked at the optimal crank angle for power production. The magneto, a self-contained generator driven by the engine, produced electrical power independent of any battery, ensuring that ignition would continue even if other electrical systems failed. Dual magnetos provided redundancy, allowing the engine to continue operating if one system failed. The propeller transmitted engine power to the air, its rotating blades functioning as wings that generated thrust rather than lift. Each blade section operated at its own airspeed, the sum of the aircraft's forward velocity and the rotational velocity at that particular radius from the hub. The blade angle needed to match this local velocity to maintain efficient operation, creating the characteristic twist from hub to tip. The propeller absorbed all the power the engine could produce, and matching propeller design to engine characteristics required balancing thrust generation against the torque capacity available at various rotational speeds. The airframe structure carried all loads and maintained the geometric relationships between components that allowed the aircraft to function. Wing spars, the primary longitudinal beams, resisted bending moments created by the difference between distributed lift forces pulling upward and concentrated weight pulling downward at attachment points. The spars were shaped with deeper sections where bending moments were greatest, tapering toward the tips where loads diminished. Ribs attached to the spars maintained the airfoil shape, preventing the covering from deforming under air pressure and distributing loads from the covering back to the spar. Compression members resisted forces that tried to push them together, and their design had to account for the tendency to buckle, to suddenly bend sideways when loaded beyond a critical threshold. The buckling strength depended on length, cross-sectional shape, and material properties in ways that made short, stocky members much stronger than long, slender ones of the same cross-sectional area. Bracing wires provided lateral support that reduced the effective length of compression members, allowing lighter structures that would otherwise need to be much heavier to resist buckling. The wire tension had to be adjusted correctly during assembly and checked periodically to ensure the structure maintained its intended geometry. Tension members, the wires and cables that pulled rather than pushed, were efficient because they could be thin without risk of buckling. Wire rope made from twisted strands of high-strength steel provided excellent strength-to-weight ratio and flexibility that allowed routing around pulleys and through fair leads. Turnbuckles allowed precise adjustment of wire length and tension, and safety provisions prevented them from loosening during operation. The attachment points, where wires connected to the structure needed to spread loads across sufficient area that local stresses remained below limits that would crush or tear the material. Control surfaces, rudder, elevators, ailerons were smaller wings that generated forces when deflected from their neutral positions. The rudder created side forces that yawed the aircraft left or right. Elevators changed the pitching moment, causing the nose to rise or fall. Ailerons deflected oppositely on the two wings, creating a rolling moment that banked the aircraft into turns. The pilot actuated these surfaces through mechanical linkages that transmitted inputs from the control stick and pedals, with the linkage geometry designed to provide appropriate control sensitivity and forces throughout the range of surface deflection. Landing gear absorbed the impact of touchdown and supported the aircraft during ground operations. The structure needed to be strong enough to withstand landing forces that could reach several times the aircraft's weight during hard impacts, yet light enough that carrying it in flight did not severely penalize performance. Springs or other energy-absorbing mechanisms cushioned the impact, preventing damage to the airframe from the sudden deceleration. Wheels or skids provided the interface with the ground, sized and positioned to prevent the aircraft from tipping over during taxiing or when subjected to crosswinds during landing. Fuel tanks stored the liquid energy that powered flight, positioned to maintain proper weight distribution as fuel was consumed. The tanks needed to be sealed against leakage while allowing air to enter as fuel was withdrawn, preventing vacuum that would stop flow. Lines carried fuel from tanks to the engine through filters that removed contaminants that might clog carburetor passages. Fuel quantity indicators gave the pilot information about remaining supply, though their accuracy was often questionable, and prudent pilots learned to verify readings through multiple means, including elapsed time calculations and direct visual inspection when possible. The flight control system translated pilot inputs into aerodynamic forces that maneuvered the aircraft. Cables ran from cockpit controls to pulleys and bell cranks that changed the direction of motion, ultimately connecting to control surface horns, where the cable tension became a force that deflected the surface. The cable routing needed to maintain adequate tension while allowing for airframe flexure and temperature changes that altered dimensions. Pulley bearings needed to rotate freely with minimal friction, and fair leads guided cables through structural members without chafing that would eventually weaken and break the cable strands. Instruments provided the pilot with information about the aircraft's state and the environment through which it moved. The airspeed indicator sensed dynamic pressure through a pitot tube facing into the airflow and compared it to static pressure sensed at a location where local airflow disturbances were minimal. The difference drove a mechanism that moved a needle across a calibrated dial showing velocity. The altimeter sensed absolute pressure through an aneroid capsule that expanded as pressure decreased with altitude, translating this expansion into needle motion that indicated height above sea level. The compass used a magnetized needle to indicate magnetic north, though the accuracy was degraded by the steel and electrical components in the aircraft that created local magnetic disturbances. Each system existed in relationship to all others, with failures in one potentially affecting several. An engine failure eliminated thrust, but also stopped the generator that powered electrical systems. Structural damage from overstress might jam control surfaces or alter the aerodynamic balance, that made flight possible. Fuel exhaustion stopped the engine, but also eliminated the weight that had been part of the aircraft's center of gravity calculation. The pilot needed to understand these interdependencies to respond appropriately when problems occurred, making decisions based on partial information under time pressure, while managing the aircraft's continued motion through the air. The diversity of early aircraft designs created a landscape where each machine was nearly unique, incorporating the particular ideas and preferences of its builder. This individuality made sense when aircraft were experimental devices built by individuals or small teams, but it became problematic as aviation expanded beyond the pioneering phase. Pilots transitioning between different aircraft needed to learn entirely new control arrangements and flight characteristics. Mechanics servicing multiple types required different tools and procedures for each. Parts from one aircraft could not be used to repair another, even when the function was identical. The military services were among the first to recognize the value of standardization. An air force operating diverse aircraft types faced logistical complexity that reduced operational readiness and increased costs. Spare parts inventories multiplied, training programs fragmented, maintenance facilities needed broader capabilities. Standardizing on fewer aircraft types simplified these challenges, and the specifications developed to guide procurement began to establish common requirements that manufacturers needed to meet. These specifications addressed performance parameters, structural strength requirements, and increasingly the interfaces and characteristics that allowed consistent operation and maintenance. Instruments standardized around layouts and scales that pilots could interpret without retraining. The primary flight instruments, airspeed, altitude, attitude, heading, occupied consistent positions on the instrument panel. The direction of needle movement for increasing values became conventional. The color coding of ranges, green for normal operation, yellow for caution, red for prohibited, provided quick visual assessment of conditions. Pilots transitioning between different aircraft encountered familiar instrument arrangements that reduced the cognitive load during critical phases of flight, when attention needed to focus on controlling the aircraft rather than interpreting unfamiliar displays. Engine mounts standardized the attachment points between engine and airframe, allowing engines to be removed and installed with consistent hardware and procedures. The mounting patterns specified bolt locations, load paths, and the provision for vibration isolation that prevented engine oscillations from transmitting excessively into the structure. Different engines with the same mount pattern could be substituted when one type was unavailable or when performance requirements changed. This interchangeability reduced the aircraft engine combination from a permanent marriage to a relationship that could be altered based on operational needs or parts availability. Propeller hubs adopted standard taper and bolt patterns that allowed propellers from different manufacturers to fit a given engine. The standardization extended to pitch mechanisms in adjustable propellers, to the electrical or hydraulic systems that controlled pitch changes, and to the mounting of spinners that covered the hub for aerodynamic cleanness. A damaged propeller could be replaced without concern that the replacement would require modifications to install or would have incompatible control interfaces. The standard also allowed propeller selection to be based on performance characteristics rather than being constrained by unique mounting requirements. Control stick and rudder pedal movements standardized so that the same pilot inputs produced the same aircraft responses across different types. Pulling back on the stick pitched the nose up. Pushing forward pitched down. Moving the stick left rolled left. Right rudder pedal yawed the nose right. These conventions became so deeply ingrained that violations of them were considered dangerous. An aircraft that responded differently would likely confuse pilots during high workload situations when responses needed to be instinctive rather than consciously considered. The standardization of control sense and sensitivity allowed pilots to operate unfamiliar aircraft with reduced risk of control errors. Radio equipment standardized around frequency bands and modulation methods that allowed communication between aircraft and between aircraft and ground stations. The physical interfaces, antenna connections, power supplies, mounting hardware became consistent so that radio equipment could be installed in different aircraft using the same procedures and fittings. The operating procedures and phraseology standardized so that communications were clear and unambiguous despite differences in equipment or operators. This standardization was essential as radio became critical for air traffic coordination and navigation. Navigation aids evolved towards systems that worked consistently across wide areas, allowing pilots to determine position and course without relying solely on visual reference to the ground. Radio beacons transmitted signals that aircraft receivers could use to determine bearing to the station. The standardization of beacon frequencies and signal characteristics allowed a single receiver to work with any beacon in the system. Later, more sophisticated systems provided distance information or created corridors that aircraft could follow. But the underlying principle remained: standardized signals and receiver characteristics that made the system universally accessible to properly equipped aircraft. Airfield facilities standardized around requirements that allowed aircraft to operate safely and efficiently regardless of location. Runway dimensions accommodated the takeoff and landing distances of the aircraft types expected to use them, with safety margins that accounted for variations in pilot technique and atmospheric conditions. Surface preparation provided adequate strength to support aircraft weights without rutting or breaking up, drainage to prevent water accumulation, and marking to indicate usable areas and boundaries. Lighting systems used standard colors and placement patterns: white lights along runway edges, green at thresholds, red at far ends, creating visual cues that were consistent worldwide. Fuel quality standards specified the characteristics required for safe engine operation. Octane ratings indicated resistance to premature ignition that would damage engines designed for higher performance fuels. Volatility specifications ensured the fuel would vaporize adequately for combustion without excessive vapor lock in fuel lines. Contamination limits protected fuel systems and combustion chambers from deposits or corrosion. Testing procedures verified compliance with these standards, and delivery systems prevented mixing of different fuel grades. Pilots could trust that fuel meeting the specification would perform correctly regardless of where it was obtained. Maintenance documentation standardized around formats that presented information consistently. Exploded diagrams showed how parts assembled, with numbering systems that corresponded to parts lists. Service procedures described tasks in sequential steps with torque specifications, tool requirements, and inspection criteria. Troubleshooting guides organized symptom diagnosis remedy information to help mechanics identify and correct problems efficiently. The standardized documentation reduced errors and improved the speed and reliability of maintenance work, particularly when performed by mechanics encountering an aircraft type for the first time. Safety wiring techniques standardized the methods for preventing fasteners from loosening due to vibration. The wire routing, twisting method, and attachment ensured that any rotation of the fastener in the loosening direction would tension the wire rather than allowing movement. The technique required skill to execute properly, but was universal enough that any trained mechanic could verify whether it had been done correctly. The standardization extended to the wire material and diameter used for different fastener sizes and load conditions, providing confidence that properly executed safety wiring would prevent failures. Inspection intervals standardized based on accumulated experience about when different components typically required examination or replacement. Time-based inspections occurred after specific numbers of flight hours, calendar-based inspections after specific periods regardless of use, and cycle-based inspections after specific numbers of operations that imposed wear or stress. The standardization of these intervals across aircraft types simplified scheduling and allowed operators to predict maintenance requirements. The intervals themselves were conservative enough to catch most problems before they led to failures, but not so frequent that excessive maintenance consumed resources unnecessarily. Training syllabi standardized the knowledge and skills required for pilots and mechanics, creating consistent baseline competencies. Ground school curricula covered aerodynamics, meteorology, navigation, regulations, and aircraft systems in sequences that built understanding progressively. Flight training progressed through stages: basic airwork, takeoffs and landings, emergency procedures, cross-country navigation, with defined completion standards at each stage. Mechanic training covered theory and practice in structures, power plants, electrical and hydraulic systems, with hands-on work that verified understanding. The standardization meant that certificates granted by one authority indicated competencies that were recognized broadly. Manufacturing quality standards specified the acceptance criteria for materials and completed components. Tensile tests verified that materials possessed adequate strength. Dimensional inspections ensured parts fit together properly. Non-destructive testing detected internal flaws invisible to visual inspection. X-rays revealed cracks in castings. Magnetic particle inspection found surface cracks in ferrous components. Dye penetrant inspection highlighted cracks in non-magnetic materials. The standardization of these quality control methods gave confidence that components met design requirements and would perform reliably in service. The accumulated effect of standardization was an aviation system where different elements worked together predictably. An aircraft manufactured on one continent could operate at airports across the globe, be maintained by locally trained mechanics using available parts and documentation, communicate with air traffic services using standard procedures and radio equipment, navigate using standardized navigation aids, and be flown by pilots whose training followed recognized standards. This interoperability was not accidental, but resulted from conscious efforts to establish and maintain standards across national boundaries and organizational lines, recognizing that aviation was inherently international and that parochial approaches would limit the utility of the system. The first aircraft appeared as curiosities, novelties that drew crowds when they flew, but seemed to have little practical application beyond spectacle and sport. The distances they could travel remained modest. The loads they could carry were minimal. Their operation required extensive ground support, and their reliability was uncertain enough that any significant journey involved risk of forced landing in unprepared locations. These limitations meant that conventional transportation, rail for long distance, vehicles for local movement, remained superior for nearly every practical purpose. Aviation existed at the margins, pursued by enthusiasts and supported by those who saw potential in what was still more promise than reality. Military interest provided the earliest sustained practical application. The ability to observe enemy positions from above offered intelligence that ground-based reconnaissance could not match. Even crewed aircraft, capable of flying only in fair weather and carrying only an observer with binoculars, provided value that justified the costs and risks. Military organizations began acquiring aircraft, not because they were cost-effective compared to alternatives, but because they provided capabilities that had no alternative. The observation role expanded gradually to include photography, artillery spotting, and communication between separated units. Tasks where the aircraft's ability to move rapidly across terrain became decisive. Mail transport emerged as another early practical application where aviation's advantages outweighed its limitations. Letters and small packages had high value relative to their weight, making the economics of air transport more favorable than for bulk cargo. The speed of delivery, measured in hours rather than days compared to surface transport, justified premium pricing that covered operating costs. Routes were established between cities with adequate facilities and sufficient mail volume, creating the first regularly scheduled air services. The flights remained vulnerable to weather cancellations and mechanical problems, but when successful, they demonstrated that aviation could provide services people would pay for. Passenger transport developed more slowly because the risks and discomforts made it unappealing to most travelers. The aircraft were noisy, cold, and prone to turbulence that caused motion sickness. Accidents, while infrequent in absolute terms, occurred at rates that made air travel statistically more dangerous than train or ship. The cost exceeded what most people could justify for the time savings achieved. Early passenger services catered to those who valued speed above comfort or cost: business travelers, government officials, others whose time was valuable enough or whose needs were urgent enough to justify the expense and accept the risks. The infrastructure to support commercial aviation appeared gradually as the volume of activity justified investment. Airports replaced open fields, providing prepared surfaces for takeoffs and landings, hangars for maintenance and weather protection, terminal buildings for passenger processing and cargo handling. Weather reporting improved, giving pilots information about conditions along routes and at destinations. Navigation aids were installed, allowing flight in reduced visibility when visual reference to the ground was inadequate. These investments reduced the operational constraints that had limited early aviation, making flights more reliable and less dependent on ideal conditions. Aircraft improved in ways that made them more suitable for commercial service. Enclosed cabins protected passengers from cold and noise. Larger engines provided power to fly higher above weather, to carry more payload, to cruise at speeds that made trips shorter. Improved instruments allowed flight in weather that would have grounded earlier aircraft. Better radios enabled communication that improved safety and coordination. Operational range increased, allowing direct flights between cities that previously required intermediate stops for refueling. Each improvement expanded the practical utility of air transport, bringing it closer to being competitive with surface alternatives. The economic model shifted from wealthy individuals or organizations subsidizing aviation as a hobby or experiment to commercial enterprises operating on revenue from services provided. Airlines purchased aircraft and hired pilots and mechanics, investing in equipment and capabilities that would generate returns over years of operation rather than being consumed in brief periods of experimentation. The transition was gradual and uneven. Some routes and operators were profitable, while others required subsidy. Some regions had adequate traffic density, while others did not. But the trend was toward aviation becoming a business rather than remaining a passion project. Public perception of aviation evolved from viewing it as dangerous adventure to accepting it as a legitimate form of transportation. Accidents still occurred and received significant attention when they did, but the absolute number of flights and the miles traveled increased faster than the accidents, improving the safety record in statistical terms. People became familiar with the sight and sound of aircraft overhead, and the novelty that had drawn crowds diminished. Aviation was becoming normal, integrated into the infrastructure of modern society, rather than existing as a separate phenomenon, practiced by daring individuals operating at the edge of what was possible. The replacement of older aircraft types happened continuously as manufacturers introduced designs with better performance or lower operating costs. Airlines retired aircraft that had been state-of-the-art just years earlier, selling them to operators with less demanding requirements or scrapping them for parts. The pace of improvement meant that the leading edge of aviation technology moved rapidly, though older designs persisted in secondary roles long after they were obsolete for mainline service. This cycle of introduction and retirement drove continuous change in the character of the fleet and in the capabilities available to operators and passengers. Pilot training evolved from informal apprenticeship to structured programs that produced consistently qualified graduates. Flight schools established curricula that covered ground subjects and flying skills in sequences that built competency systematically. Standardized check rides verified that students met defined proficiency standards before receiving licenses or ratings. Simulator training began to supplement actual flight time, allowing practice of emergency procedures that would be too dangerous to perform in real aircraft. The professionalization of pilot training produced operators with more uniform baseline skills and knowledge, improving safety and making pilot qualifications more transparent to employers and regulators. Mechanics became specialized in aircraft systems as the complexity exceeded what generalists could master. Engine specialists understood the intricacies of power plants. Propeller specialists dealt with variable pitch mechanisms and blade tracking. Instrument specialists calibrated and repaired the growing array of cockpit devices. Radio specialists maintained communication and navigation equipment. Airframe specialists handled structures and control systems. This specialization improved the quality of maintenance while requiring larger organizations to staff all the necessary capabilities. Small operators either sent work to specialized shops or accepted limitations in the maintenance they could perform in-house. Regulations expanded to cover aspects of aviation that were unregulated in the early years when activity levels made detailed rules unnecessary. Airspace was classified by use and restrictions, with some areas prohibited or restricted for security or safety reasons. Flight rules were established for different conditions. Visual flight rules when visibility was adequate, instrument flight rules when it was not. Equipment requirements specified what instruments and systems aircraft needed for different types of operations. Operator certification verified that airlines had adequate facilities, procedures, and oversight to conduct commercial services safely. The regulatory framework grew more comprehensive and prescriptive as the industry matured. Insurance shifted from being unavailable or prohibitively expensive to being routine and required for commercial operations. The development of actuarial data allowed insurers to price risk with some confidence, and the premiums became predictable costs that operators included in their business plans. Liability coverage protected against claims from passengers or people on the ground injured by aircraft operations. Hull coverage protected against loss of the aircraft itself from accidents or other causes. The availability of insurance at reasonable rates indicated that aviation had become sufficiently well understood and statistically predictable that financial institutions would accept the risks. The workforce expanded far beyond pilots and mechanics to include dispatchers who planned routes and monitored flights, meteorologists who interpreted weather data and briefed crews, schedulers who optimized aircraft utilization and crew assignments, sales staff who marketed services and processed bookings, ground handlers who serviced aircraft between flights. The airline became a complex organization requiring coordination across multiple functions, and the management skills needed to run successful operations resembled those required in other large service businesses. Aviation had matured from technical challenge to business enterprise. Manufacturing consolidated as the capital requirements for developing and producing competitive aircraft exceeded what small enterprises could raise. Larger manufacturers absorbed smaller ones or drove them from the market through superior products or lower costs achieved through volume production. The consolidation reduced the diversity of aircraft types while increasing the resources available for development of more capable designs. Standardization benefited from fewer manufacturers producing to their own internal standards that became de facto industry standards as their market share grew. International cooperation increased as airlines flew routes crossing national boundaries, and as aviation safety and efficiency benefited from harmonized standards. Treaties established rules for overflight rights, technical standards, and the recognition of licenses and certifications across borders. International organizations coordinated the development of standards for everything from radio frequencies to instrument approach procedures. The cooperation was sometimes contentious as nations balanced their sovereignty against the benefits of harmonization. But the trend was toward greater international alignment as the utility of aviation depended on its ability to connect distant places across political boundaries. The transformation was nearly complete. Aviation had transitioned from experimental pursuit to established industry. The change happened gradually enough that no single event marked the completion. But the evidence was clear in the statistics of passengers carried, mail delivered, hours flown, aircraft produced, people employed. What had seemed impossible within living memory had become routine, and the younger generation grew up in a world where air travel was simply one among several transportation options rather than a marvel that defied the natural order. The pioneers who remembered when flight was a dream were becoming fewer. Their experiences preserved mainly in records and memories that captured a time when humans first learned to navigate the realm that had belonged exclusively to birds and insects since the origin of life on Earth. The network of airports that made commercial aviation practical required investment in land, construction, and equipment on a scale that exceeded the resources of private operators. Governments recognized that aviation infrastructure served public purposes, facilitating commerce, enabling communication, supporting defense, and funded development that would not have happened through market forces alone. The location of airports reflected considerations of land availability, proximity to population centers, terrain suitable for approach and departure paths, and compatibility with surrounding land uses. Flat terrain was preferred for obvious reasons. But coastal cities, or those in mountainous regions, had to work with less ideal topography. Runways grew longer and stronger as aircraft became heavier and faster. The early grass fields adequate for light aircraft could not support the weight of multi-engine transports or provide the smooth surface needed for high-speed operations. Paved runways used concrete or asphalt several inches thick over prepared foundation layers that distributed weight to prevent deformation. The surface needed to shed water quickly to prevent hydroplaning during wet conditions, requiring careful grading and drainage systems. Grooves cut into the pavement improved traction. The pavement edges needed to support aircraft that occasionally departed the center line, and shoulders beyond the edges provided additional safety margins. Lighting systems allowed night operations that would otherwise have been limited to daytime hours. Edge lights outlined the runway boundaries, showing pilots where usable pavement ended. Approach lights extended beyond the threshold, providing visual guidance during descent, when the runway itself might not be visible until the final moments before landing. Threshold lights marked the beginning of available landing surface. End lights indicated where usable distance terminated. The intensity could be adjusted to suit visibility conditions: bright during clear weather, dimmed when low clouds created glare. Backup power systems ensured lighting remained available even when primary electrical service failed. Terminal buildings processed passengers and cargo between ground and air transport, providing ticketing, baggage handling, waiting areas, and connections to surface transportation. The design needed to separate arriving and departing flows, provide security screening, handle peak loads without excessive congestion, and present an image that reflected the airline's or airport's identity. The buildings grew larger and more complex as traffic volumes increased, evolving from simple sheds to elaborate structures that became architectural landmarks. The layout affected operational efficiency. Long walks between gates and facilities frustrated passengers. Inadequate space created bottlenecks. Poor signage caused confusion. Hangars sheltered aircraft during maintenance and protected them from weather when not in service. The span of the structure needed to accommodate aircraft wingspans that could exceed 100 feet, requiring either massive central supports or clear span designs that eliminated internal columns. Doors needed to be large enough for aircraft to enter and exit, operated by mechanisms that could handle their weight and size. The interior needed adequate lighting for detailed inspection work, heating to allow comfortable working conditions during cold weather, and ventilation to remove exhaust when engines needed to run indoors. Storage for parts, tools, and equipment consumed additional space. Fueling facilities stored aviation fuel in underground tanks that held thousands of gallons, protected from temperature extremes and contamination. Pumping systems transferred fuel to aircraft through hoses or hydrant systems built into the apron pavement. Filters removed water and particles that could damage engines or clog fuel system components. Grounding cables prevented static electricity buildup during fueling operations that could ignite fuel vapors. Quality control procedures tested fuel regularly to verify it met specifications. The logistics of keeping adequate fuel inventory while managing storage capacity and supply deliveries required careful planning, particularly at locations distant from refineries or distribution centers. Control towers provided the elevated vantage point that allowed controllers to observe aircraft movements on the ground and in the vicinity of the airport. The visibility from the tower cab needed to extend across the entire airfield, requiring placement and height that eliminated blind spots. Radio equipment allowed communication with pilots, and telephone connections linked controllers to other facilities. Binoculars aided in identifying distant aircraft and reading registration markings. Later, radar displays supplemented visual observation, showing aircraft positions and trajectories beyond visual range. The tower operated continuously during airport operating hours, coordinating traffic to maintain safe spacing and efficient flow. Weather observation facilities measured conditions critical to flight operations: wind speed and direction, visibility, cloud height, temperature, pressure. The observations were recorded at regular intervals and transmitted to pilots, controllers, and meteorologists. Automated systems measured and reported conditions without human intervention, improving consistency and reducing workload. Wind measurement was particularly important as crosswinds beyond certain limits exceeded the control authority available to pilots during takeoff and landing. Changing weather could force operations to shift between different runways to maintain headwind components within acceptable ranges. Navigation aids created invisible pathways through the sky that aircraft could follow without visual reference to the ground. Radio beacons transmitted signals that aircraft receivers used to determine bearing to the station, allowing pilots to navigate toward or away from known locations. Range arcs from multiple stations intersected at points that defined position, though the accuracy diminished with distance from the stations. The beacons were positioned along airways, designated routes connecting major airports, creating a network of radio highways that aircraft followed in instrument conditions. Instrument landing systems provided precision guidance during approach to landing when visibility was too poor for visual reference to the runway. The system transmitted two radio beams, one defining the horizontal approach path aligned with the runway centerline, the other defining the vertical descent angle that would bring the aircraft to the threshold at a safe altitude. Cockpit instruments displayed deviations from these beams as needle deflections that pilots corrected by adjusting heading and descent rate. The system allowed approaches in weather that would otherwise require diversion to alternate airports or waiting for conditions to improve. Radar systems detected aircraft at ranges and in conditions where visual observation was impossible. The radar antenna rotated continuously, transmitting pulses of radio energy and receiving echoes reflected from aircraft. The time delay between transmission and echo indicated distance. The antenna direction, when the echo was received, indicated bearing. The combined information placed the aircraft at a specific point relative to the radar site. Controllers use this position information to maintain safe separation between aircraft, to provide traffic advisories, and to guide lost or disoriented pilots toward airports. The radar coverage extended outward to distances limited by terrain, the curvature of the Earth, and the sensitivity of receiving equipment. Airways defined the structure of airspace, creating routes that aircraft followed between departure and destination points. The airways connected navigation aids, forming a network similar to the highway system on the ground, but extending through 3 dimensions. Different altitudes were assigned for different directions of travel, maintaining vertical separation between opposing traffic flows. The airway system provided predictable routing that simplified flight planning and allowed controllers to manage traffic with knowledge of where aircraft would be along their routes. Aircraft flying outside the airway system needed special clearances and often faced restrictions designed to maintain separation from those following established routes. Communication networks linked aircraft, towers, en route control facilities, and flight service stations through radio and telephone connections. Pilots reported positions, requested clearances, received instructions, and obtained weather information through these channels. Controllers coordinated handoffs as aircraft moved between sectors, issued traffic advisories, and provided assistance when problems occurred. The standardization of phraseology and procedures allowed efficient communication despite the variety of accents and native languages among international operators. Recording systems captured all radio transmissions, providing records useful for training and investigation of incidents. Maintenance facilities at airports provided services ranging from routine inspections to major overhauls. Line maintenance handled minor problems that could be corrected quickly between flights. Replacement of failed components, replenishment of fluids, adjustment of systems. Base maintenance performed scheduled inspections and more complex repairs, requiring specialized equipment and longer downtime. The facilities needed parts inventory, technical documentation, qualified mechanics, and supervisory oversight to ensure work met standards. Larger airports supported multiple airlines and aircraft types, requiring broader capabilities than single operator facilities. Meteorology centers collected weather observations from widespread sources, analyzed the data to produce forecasts, and disseminated information to operators. Surface observations from airports provided current conditions. Upper air data from balloon-launched instruments gave temperature, pressure, and wind at various altitudes. Satellite imagery showed cloud patterns and storm systems. Forecasters interpreted this information to predict conditions along routes and at destinations, updating their assessments as new data became available. The forecasts were never perfect, but they provided guidance that allowed operators to make informed decisions about whether flights could be conducted safely. Emergency services positioned fire and rescue equipment at airports to respond to accidents or incidents. Fire trucks carried foam and water for suppressing fuel fires, with capacity and flow rates adequate for the largest aircraft operating from the field. Medical equipment and trained personnel provided initial treatment for injured passengers or crew. Crash axes and other tools allowed rescuers to penetrate damaged aircraft structures to reach trapped occupants. The response capability was sized based on the aircraft type served and regulatory requirements, with larger airports maintaining correspondingly larger emergency resources. Regular training exercises maintained readiness and identified deficiencies in equipment or procedures. The infrastructure created a system where aviation operations could occur with reliability and safety that commercial service required. The physical facilities, runways, buildings, equipment represented visible investment, but equally important were the procedures, standards, and trained personnel that made the infrastructure functional. An airport was not merely a place where aircraft landed and departed, but a node in a network that connected the surface to the air, the local to the distant, the present to destinations that would be reached in hours rather than days. The infrastructure both enabled and constrained what was possible. Aircraft could fly only where facilities existed to support them, but where adequate infrastructure was present, the possibilities expanded dramatically. The compression of distance that aviation achieved altered the relationship between places separated by oceans or continents in ways that surface transportation could never match. A journey that required weeks by ship became hours by aircraft, collapsing the experiential distance between continents to intervals shorter than many domestic train journeys. This compression was not merely quantitative, but qualitative. It changed what seemed possible, what seemed near, what could be accomplished within the constraints of human lifespans and professional careers. Cities on opposite sides of the globe became connected by regular flights that made international presence practical for organizations that previously could only operate regionally. Business operations expanded geographically as executives could visit distant facilities, meet with clients, inspect operations, and return within timeframes that made such trips routine rather than exceptional. The ability to maintain direct personal contact across vast distances allowed companies to coordinate activities globally rather than delegating authority to local managers who operated with substantial autonomy due to communication delays. Decisions that previously would have been made locally with headquarters, informed afterward, could now involve real-time consultation with central management. The organizational structure of international enterprises shifted to reflect the reduced friction of distance that aviation provided. Diplomatic activity accelerated as government officials could meet face-to-face without the lengthy absences from their home countries that ship travel required. International conferences gathered participants from dozens of nations for discussions that would have been impractical when travel time consumed weeks. Crisis response improved when relevant decision-makers could assemble quickly rather than waiting for slow ships to deliver them to negotiation sites. The conduct of international relations adapted to the assumption that travel between capitals was measured in hours, and the pace of diplomatic activity increased correspondingly. Cultural exchange intensified as artists, performers, scholars, and athletes could tour internationally without the extended commitments that ship travel demanded. A musician could perform in multiple countries within weeks. An athlete could compete in events scattered across continents throughout a season. A scholar could present research at conferences worldwide and maintain teaching responsibilities at home. The exposure to diverse cultural products and practices increased as the people who created and performed them became more mobile. This circulation of ideas and artistic works contributed to both greater cosmopolitanism in major centers and concern in some quarters about cultural homogenization. Tourism expanded beyond the wealthy few who could afford extended leisure time and expensive ship passages. The middle class gained access to international travel as airfares declined and as the time required decreased to levels compatible with typical vacation durations. Destinations that had been exotic and remote became accessible, and the tourism industry that developed to serve these visitors became economically significant in regions that attracted large numbers of visitors. The environmental and cultural impacts of mass tourism generated debates about whether the economic benefits justified the disruptions to local communities and ecosystems. Migration patterns changed as the cost and difficulty of international relocation decreased. Families separated by immigration could maintain contact through visits that were impractical when reunion required ocean voyages. Professional migration became more fluid as people could accept positions in distant countries while maintaining connections to their places of origin through periodic return visits. The psychological distance of emigration diminished when the possibility of return was measured in hours of flight time rather than weeks at sea. Diasporas maintained stronger cultural and social ties to origin countries than had been possible in previous generations. Scientific collaboration accelerated as researchers could visit colleagues' facilities, attend specialized conferences, and maintain projects requiring coordination between institutions on different continents. The exchange of ideas happened through direct interaction rather than only through correspondence that delayed communication by weeks or months. Equipment and samples could be transported when personal courier service was necessary to ensure proper handling. The practice of science became more international as the barriers of distance diminished, though language differences and visa restrictions remained obstacles that aviation could not eliminate. Emergency response gained capabilities that saved lives and reduced suffering. Medical evacuations transported seriously ill or injured people to facilities with specialized capabilities that might not exist nearby. Disaster relief delivered personnel and supplies to affected areas within hours rather than days, improving outcomes through earlier intervention. The coordination of international assistance became practical when responders and equipment could be moved rapidly to wherever need was greatest. The global humanitarian system that developed assumed aviation as fundamental infrastructure, without which rapid response would be impossible. Economic integration deepened as the cost of coordinating activities across distances declined. Supply chains extended globally as manufacturers sourced components from locations offering cost advantages, trusting that aviation could deliver time-critical parts quickly when needed. Financial markets operated across time zones, with traders and analysts traveling to maintain personal relationships that facilitated deals. The location of production became more flexible as the need for proximity to markets diminished for products where transportation cost was small relative to value. Economic geography reorganized around the logic of comparative advantage, untempered by the costs that distance had previously imposed. News gathering accelerated as journalists could reach distant events quickly and file reports, while situations were still developing, rather than after outcomes were determined. Television networks stationed correspondents in major cities worldwide, flying them to breaking stories with equipment that allowed immediate broadcasting. The audience's awareness of distant events increased as coverage became more immediate and comprehensive. The interpretation of global events was influenced by which stories received coverage and how they were framed. And aviation's role in enabling rapid deployment of journalists affected what the public learned about the wider world. Military operations gained global reach as forces could deploy to distant theaters within days rather than the weeks or months that ship transport required. The ability to project power quickly influenced strategic calculations and alliance structures. Air superiority became essential because control of airspace determined whether supplies and reinforcements could reach ground forces. The logistics of sustaining military operations in distant locations relied fundamentally on airlift capacity that could deliver the volume of material modern forces consumed. The character of conflict changed as distance ceased to provide the protection it had offered throughout most of human history. Pandemic response capabilities improved through rapid deployment of medical teams and supplies, though aviation also facilitated disease spread by transporting infected individuals across continents before symptoms appeared. The balance between mobility's benefits for response and its risks for transmission required careful management during outbreaks. Quarantine measures that had been effective when travel was slow became less reliable when travelers could cross oceans during disease incubation periods. The globalization of health risks paralleled the globalization of commerce and culture, creating interdependencies that made purely national approaches to disease control insufficient. Environmental monitoring gained global coverage as scientists could deploy instruments in remote locations and return to service them, as research teams could reach field sites regardless of distance from their institutions, and as samples could be transported while still fresh enough for analysis. The understanding of global systems, ocean circulation, atmospheric chemistry, ecological relationships spanning continents, advanced through research that aviation made practical. The irony that aviation contributed to the environmental changes being studied was not lost on researchers who depended on it for their work, but recognized its role in the problems they documented. Sports became truly international as leagues and competitions included teams from multiple continents, made practical by air travel that allowed regular season schedules despite vast distances between venues. Athletes competed at a global level rather than being constrained to regional competition with occasional international tournaments. The economic model of professional sports shifted to accommodate the travel requirements, and the sporting calendar reorganized around the assumption that teams could cross continents between games. Fans followed teams and athletes from around the world, facilitated by the broadcast coverage that aviation enabled through rapid deployment of production equipment and personnel. The perception of Earth itself changed as aviation made experiential the notion that all places were part of a single connected system, rather than separate worlds divided by unbridgeable distances. The photographs of Earth from high altitude that aviation made possible showed the planet as a single entity suspended in space, an image that influenced environmental consciousness and internationalist political movements. The realization that one could leave any point on Earth and reach any other point within 2 days at most diminished the psychological size of the planet and strengthened awareness of human interconnection and shared fate. The future trajectory pointed toward increased connectivity as aviation capacity continued expanding and as costs continued declining relative to incomes. More people would gain access to international travel. More goods would move by air. More activities would assume rapid mobility as normal rather than exceptional. The limitations were not primarily technical, but environmental and infrastructural. The atmosphere's capacity to absorb emissions, the availability of suitable airport sites near major cities, the social acceptance of noise and other impacts. These constraints would shape how aviation's role evolved, but seemed unlikely to reverse the integration that had already transformed human geography from a world of separated regions to a globally connected system where distance retained significance but had lost much of its power to isolate. Flight altered the human relationship with space in ways that extended beyond mere transportation. The experience of rising above the surface, of seeing the world from a perspective previously accessible only to imagination, changed how people understood their place within physical reality. The landscape that seemed vast and dominant when traversed at ground level revealed itself from altitude as a comprehensible pattern, its features organized into relationships visible only from above. Rivers appeared as coherent systems rather than isolated crossings. Mountain ranges revealed their structure. Cities showed their plans and boundaries. This elevated perspective provided a literally broader view that influenced how people thought about territory, boundaries, and the organization of space. The sensation of flight itself carried psychological dimensions that pilots described but struggled to fully articulate. The moment of leaving the ground represented a transition from one domain to another, from the solid and permanent to the fluid and temporary. The aircraft became a small world unto itself, moving through air that offered no fixed reference, no permanent features, nothing to grasp. The experience required trust in instruments and procedures because the senses that evolved for surface existence could not be fully relied upon. Horizons tilted deceptively. Motion felt uncertain. Up and down became ambiguous in clouds or darkness. Learning to fly meant learning to distrust certain instincts and rely instead on training and reason. The view from altitude reduced human works to scale that revealed their true proportion relative to natural features. Cities that seemed to dominate their regions appeared as small patches when seen from above, surrounded by vastness that dwarfed them. The straight lines of roads and field boundaries contrasted with the organic curves of rivers and coastlines, showing where human ordering had been imposed on terrain. The patchwork of different land uses, agriculture, forest, urban development, revealed patterns of human activity that were invisible from within. This perspective could inspire both wonder at human accomplishment and humility at its limited extent. The speed of flight compressed time in ways that changed the meaning of distance. Places that had seemed impossibly remote became reachable, and this accessibility altered their psychological status from foreign to merely distant. The world seemed smaller, not because its physical dimensions changed, but because the time required to traverse it decreased below thresholds that had made certain journeys impractical or unthinkable. A distance that represented a lifetime barrier when measured in days of travel became routine when measured in hours, and this transformation reshaped ambitions and possibilities. People could envision lives that spanned continents, careers that required global mobility, relationships maintained across oceans. The democratization of altitude, the ability of anyone with means to purchase a ticket to experience what had been accessible only to birds, represented a kind of breaking of natural limits. For most of history, humans had been bound to the surface by their biology, able to climb to heights, but never to move freely through the space above. Flight eliminated this constraint, at least temporarily, offering hours of existence in a realm that had been permanently forbidden. The experience could be routine for frequent travelers, yet retained an element of the extraordinary. Humans were not built for this, yet here they were, suspended thousands of feet above the ground, traveling at speeds their bodies could never achieve unassisted. The risk inherent in flight never entirely disappeared, despite improvements in safety. Every flight required trusting that thousands of components would continue functioning correctly, that fuel would burn properly, that air would flow over wings as physics predicted, that pilots would make correct decisions, that ground controllers would provide accurate guidance. The ordinary experience of flight masked the underlying reality that survival depended on continuous, proper operation of complex systems in an environment hostile to human life. Accidents, when they occurred, often killed everyone aboard, eliminating the possibility of partial survival that characterized most ground transportation accidents. This absolute consequence of failure gave aviation a psychological weight that statistics alone could not fully capture. The environmental cost of aviation, the fuel consumed, the emissions produced, the noise generated, raised questions about whether the benefits justified the impacts. The convenience and speed that made aviation valuable came at prices paid by those who neither flew nor necessarily benefited from aviation's existence. The distribution of these costs and benefits was not uniform. Those who flew most were often those whose economic and geographic positions gave them greatest access, while impacts fell on communities near airports and on the global atmosphere that absorbed emissions. The ethical dimensions of this distribution remain contested, with no consensus about whether the system as structured was just or required reform. The cultural meanings attached to flight varied across contexts and communities. For some, aviation represented modernity, progress, connection to the wider world. For others, it represented disruption, environmental degradation, the erosion of local distinctiveness through homogenizing global culture. The pilots and aviation workers often felt deep attachment to their profession, deriving meaning from the technical mastery it required and the service it provided. Passengers might feel anything from enthusiasm to anxiety to indifference. The diversity of responses reflected how flight intersected with different values and different positions within social and economic structures. The ownership and control of aviation infrastructure reflected broader patterns of power and wealth. Major airports required land and capital that only governments or large corporations could marshal, and decisions about where to build and how to develop affected regional economies and communities in profound ways. The routes that airlines chose to serve determined which places would be well connected and which would remain peripheral to global networks. The concentration of aviation capacity in major hubs created inequalities between those near these nodes and those distant from them, replicating and sometimes amplifying existing patterns of advantage and disadvantage. The sovereignty questions raised by aviation: who controlled the airspace above territory? What rules governed flight over international waters? How disputes about air rights would be resolved required international frameworks that transcended traditional notions of territorial authority. The sky could not be divided and patrolled like land borders, yet nations asserted control over the airspace above their territory. The treaties and organizations that managed these claims represented a form of global governance that operated alongside and sometimes in tension with national sovereignty. The system worked imperfectly, but well enough to allow extensive international aviation, though conflicts erupted when political disputes led to airspace closures or routing restrictions. The aesthetics of flight influenced architecture, art, and design beyond aviation itself. The streamlined forms developed for aerodynamic efficiency became visual motifs applied to objects that would never fly: trains, buildings, consumer products, because they signified modernity and technological sophistication. The view from aircraft windows inspired photographers and painters who captured landscapes from perspectives unavailable through any other means. The airports themselves became architectural statements, their designs intended to express the forward-looking character of aviation and the ambitions of the cities they served. The cultural influence of flight extended into domains far removed from its practical applications. The temporal experience of flight created its own peculiar qualities. The hours spent in transit existed outside normal routines, neither fully part of the departure point, nor yet arrived at the destination. Passengers occupied a liminal space where productivity was difficult, entertainment was limited, and the primary activity was waiting for arrival. The boredom this generated for some was for others a valued opportunity for thought, reading, or rest unavailable in ordinary life. The experience of crossing time zones compressed or expanded the subjective day, creating jet lag that reminded travelers their bodies evolved for surface existence within single time zones, not for rapid longitudinal displacement. The class divisions within aviation made inequality visible and experiential. Passengers in different cabins received dramatically different service despite traveling on the same aircraft to the same destination at the same time. The physical separation of classes, curtains, different boarding procedures, separate lavatories, emphasized the distinctions. The pricing structures that made premium cabins accessible mainly to business travelers or the wealthy reinforced existing social hierarchies. The existence of these divisions within the supposedly modern and meritocratic domain of aviation suggested that technological progress did not automatically produce social equality. The future of flight raised questions about sustainability and limits. The dependence on fossil fuels seemed increasingly problematic as awareness of climate change grew, yet no alternative power source offered comparable energy density or operational convenience. The growth trajectory of aviation appeared incompatible with the emissions reductions required to stabilize climate, creating tension between the value placed on mobility and the need to limit environmental damage. Whether technology could solve this through more efficient engines or alternative fuels, or whether limits on aviation growth would become necessary, remained unresolved. The philosophical question of whether flight represented genuine progress or merely change with ambiguous implications had no definitive answer. The case for progress emphasized the connections enabled, the lives saved through rapid medical transport, the economic development facilitated, the personal growth that came from experiencing different places and cultures. The case for skepticism noted the environmental costs, the disruption of communities near airports, the contribution to inequality and cultural homogenization, the question of whether speed and mobility actually improved human flourishing or merely accelerated life without adding meaning. The lived reality was that flight had become integrated into the fabric of modern existence for much of humanity, taken for granted by those with regular access and aspired to by those without. The dreams that had inspired the pioneers had been realized and surpassed. Humans could fly faster and farther than they had imagined. What they had achieved transformed not just how people moved, but how they conceived of distance, time, possibility, and their relationship to the planet they inhabited. The aerial perspective would remain a fundamental part of human experience going forward, shaping consciousness in ways that surface-bound ancestors could not have anticipated, and that even those living with routine flight did not fully comprehend. The question was not whether the transformation was complete, but what would emerge from the world that flight had made possible. The refinement of existing patterns seemed more likely than radical departure from the trajectory aviation had followed since its practical beginning. Aircraft would become more efficient through incremental improvements in aerodynamics, materials, and propulsion systems that extracted more transportation from each unit of fuel consumed. The gains would accumulate gradually, a few percent here, a few there, never dramatic in isolation, but substantial when compounded over years of development. Manufacturers pursued these improvements because operating costs mattered to airlines and because regulatory pressure to reduce emissions created incentives beyond pure economics. The shift toward jet propulsion represented one of the more significant changes in the technical character of flight, altering not just the machinery, but the economics and possibilities of aviation. The jet engine achieved thrust by accelerating a mass of air rearward, using continuous combustion rather than the reciprocating cycles of piston engines. The absence of pistons, connecting rods, and crankshafts reduced mechanical complexity and vibration. The power-to-weight ratio exceeded what piston engines could achieve, allowing higher speeds and altitudes. The smoothness of operation improved passenger comfort and reduced fatigue for crews on long flights. The development of jet engines followed decades of theoretical work and experimentation that gradually solved the problems inherent in the concept. The turbine blades needed to withstand temperatures and stresses that exceeded capabilities of ordinary alloys. The compressor stages needed to pressurize incoming air without stalling or surging. The combustion chambers needed to burn fuel continuously at high temperatures without flaming out. The matching of all these components into systems that operated reliably across varying conditions and power settings required understanding of thermodynamics, fluid dynamics, and materials science at levels that earlier aviation had not demanded. The adoption of jet propulsion transformed commercial aviation by enabling speeds and ranges that piston-powered aircraft could not match economically. Flights that previously required intermediate stops for refueling became non-stop journeys. Travel times between distant cities decreased by hours. The higher operating altitudes placed aircraft above most weather, smoothing rides and improving reliability. The operating costs per seat mile decreased despite higher fuel consumption because the increased speed allowed more productive use of each aircraft. airlines could offer transcontinental and intercontinental service that competed favorably with surface alternatives on time, even after accounting for airport access. The infrastructure adapted to accommodate jet aircraft with their different performance characteristics and requirements. Runways lengthened to provide adequate takeoff and landing distances for aircraft operating at higher speeds. Pavement was strengthened to support greater weights, concentrated on smaller landing gear footprints. Terminals were redesigned to handle larger passenger volumes and provide the amenities that longer dwell times required. Air traffic control procedures evolved to manage aircraft traveling at speeds that reduced the time available for decision and communication. The investment required was substantial, but justified by the traffic growth that jet service generated. The noise produced by jet engines created friction with communities near airports, leading to restrictions on operations during nighttime hours and requirements for noise abatement procedures during arrivals and departures. The engines themselves evolved toward designs that reduced noise through higher bypass ratios that moved more air at lower velocities, through acoustic treatments that absorbed sound, and through operational techniques that minimized exposure of populated areas to high power settings. The trade-offs between noise reduction and performance or efficiency constrained how much could be achieved, but the trajectory was toward quieter operations that would reduce conflicts with residential areas. The question of alternative fuels gained urgency as petroleum supplies seemed finite and as environmental concerns about combustion emissions intensified. Synthetic fuels produced from various feedstocks offered one path, potentially compatible with existing engines and infrastructure if their properties could be made sufficiently similar to conventional jet fuel. Electric or hydrogen propulsion represented more radical alternatives that would require fundamental redesign of aircraft and ground support systems. The energy storage problem, carrying enough electric charge or hydrogen to power long flights, appeared formidable given the energy density advantages that liquid hydrocarbons provided. Whether these alternatives would prove practical remained uncertain. Automation increased as electronic systems assumed functions previously performed by human crew members. Autopilots maintained heading and altitude, reducing pilot workload during cruise. Navigation systems computed position and displayed it on moving maps, eliminating much of the manual calculation that earlier navigation required. Engine monitoring systems alerted crews to abnormal conditions, reducing the need for constant scanning of gauges. The trend was toward aircraft that could execute most phases of flight automatically, while human pilots supervised and intervened when situations exceeded the automated system's capabilities, or when judgment required human evaluation of options. The growth in passenger numbers seemed likely to continue as global economic development brought aviation within reach of populations that previously could not afford it. The number of people who had never flown exceeded those who flew regularly, suggesting vast potential for expansion as incomes rose and as service extended to underserved regions. This growth would strain infrastructure at popular destinations and along congested routes, requiring investment in additional capacity or acceptance of constraints that would limit how much expansion could occur. The environmental impact of vastly increased aviation activity raised questions about whether such growth was sustainable or desirable. The concentration of aviation capacity in hub airports created efficiency for airlines through consolidation of traffic, but increased connection times and complexity for passengers whose journeys required changing aircraft. The hub and spoke model allowed service to markets that could not support direct flights, but at the cost of longer total journey times for many travelers. Alternative models using point-to-point service offered directness, but only where traffic density justified it. The balance between these approaches shifted as aircraft economics changed and as passenger preferences influenced which services succeeded commercially. The international governance of aviation faced challenges from the tension between the need for global standards and coordination versus national desires to protect their own industries or control their airspace according to domestic priorities. The organizations that managed aviation standards and policies operated through consensus that sometimes meant slow adaptation to changing conditions. The emergence of new aviation powers with different interests from those that had dominated aviation historically created pressures for reforms to governance structures that reflected earlier distributions of capability and influence. The training of pilots adapted to aircraft with extensive automation, raising questions about maintaining manual flying skills that might be needed if automated systems failed. The balance between teaching fundamental stick and rudder abilities versus teaching management of automated systems shifted toward the latter. Though accidents attributable to automation dependency prompted reconsideration of how much manual proficiency needed to be maintained. Simulators allowed practice of emergency procedures too dangerous to perform in actual aircraft, but simulator training could not fully replicate the psychological and physical sensations of real flight, particularly in high-stress situations. The security environment surrounding aviation tightened as the vulnerability of aircraft to hostile action became apparent through incidents that demonstrated the consequences of inadequate screening and access control. The measures implemented to reduce these risks, passenger screening, baggage inspection, restricted areas, added time and inconvenience to travel while improving safety against specific threats. The balance between security and convenience remained contested, with different jurisdictions making different trade-offs based on their assessment of risks and their tolerance for impositions on passengers and operators. The economics of aviation shifted as competition intensified and as business models evolved to reduce costs. The unbundling of services that had been included in base fares allowed airlines to offer lower entry prices while collecting additional revenue from passengers who wanted amenities. The result was increased price discrimination, where passengers paid different amounts for functionally similar transportation based on timing, flexibility, and willingness to accept restrictions. The system produced lower average fares, but more complexity, and often reduced satisfaction among passengers who felt nickel and dimed by separate charges for services previously included. The environmental accounting of aviation became more comprehensive as understanding grew about the climate impact of high-altitude emissions beyond the direct contribution of carbon dioxide. The contrails produced by aircraft at cruise altitudes affected radiative balance in ways that amplified warming beyond what fuel combustion alone would produce. The full climate cost per flight was higher than simple carbon accounting suggested, complicating efforts to price environmental impacts accurately or to compare aviation with surface alternatives. The research continued, but the implications for policy remained debated. The future held both promise and uncertainty. Aviation had proven itself capable of continuous improvement across decades of development, suggesting that technical progress would continue. Yet the challenges ahead, environmental limits, infrastructure constraints, security threats, social equity questions, seemed more resistant to purely technical solutions than the engineering problems that had dominated earlier eras. Whether aviation would continue expanding indefinitely, whether it would reach a plateau limited by environmental or practical constraints, or whether it would contract under pressures that made its current scale unsustainable, remained unclear. What was certain was that aviation had fundamentally altered human existence in ways that would not be easily reversed. Multiple generations had grown to maturity in a world where flight was ordinary, where distance measured in thousands of miles was traversable within a day, where the far side of the planet was reachable within the span of a waking period. The human species had become aerially mobile, and this mobility had reorganized patterns of settlement, commerce, culture, and consciousness in ways that would persist regardless of what specific technical forms aviation might take in coming decades. The dream of flight that had seemed impossible within living memory had been so thoroughly realized that its impossibility was what now seemed unimaginable. The sky that had been the domain of birds had become a highway for humans, and that transformation would remain one of the defining achievements and challenges of the era in which it occurred. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.